So I want to start off this course framing our brains and talking about the motivation for statistics and how it's used, some definitions, and how it's applied in the real world. And so first and foremost, we want to use statistics, more specifically inferential statistics, when we have a small sample of data. And we want to use the small but random sample, that's very important for it to be random, small but random sample. We want to use it to be able to draw conclusions about the general population, the population at large. And so we may not always have our hands on the entire population. That may not be possible, but maybe we can take a random sample of say 50 or 100 and compute the mean, compute other statistics on the sample, and then using statistical methods, inferential statistical methods, be able to make really intelligent predictions or conclusions about the larger population, just using the small sample from it. And so statistics is broken up into two branches, and we're going to talk about them. We're going to talk about descriptive statistics, where we're simply just summarizing and visualizing our data, which you'll see this in data science. You'll see this as the exploratory data analysis step. It's very important, and it's where a lot of the hypothesis generation comes from. Inferential statistics is what we were just talking about, where we're trying to make predictions or draw conclusions about the larger population just based on a tiny sample that we have. It may not be tiny, but we want to be able to take this random sample and say something about the population. So there's some common packages for doing statistics. R is probably the most famous one, I believe. And you can also use Python to help manipulate data, visualize it, and there's a lot of open source packages that you can use for statistical testing. This is a course on statistics, but probability is an important component of it. A lot of the statistical methods that we use rest on probability theory, assuming independence, random samples, and those sorts of things. And we'll get into that. We won't talk about it now, but I wanted to frame our brains as to what statistics is, why we use it, what are the two branches, what are some softwares out there that we can use, and then also talk about how probability is actually involved in statistics. So before we dive too far into the world of statistics, the first thing we need to really kind of understand is the different types of data that we'll be working with. Since in statistics we're working with data, it's going to be very important to know which types of data we're working with, because it's ultimately going to determine the types of analysis we do on our data. And so there's two types of data. There's the two most common is numerical and categorical. So your numerical data is going to be like we have in the example right here. It's going to be something like your test scores. These are going to be real numbers or integers of some fashion. And test scores is going to be like, you can get a 73 or an 82 or a 91 or 100 or something like that. That's a numerical data type. Like I said, it can be discrete, like an integer, it's countable, or it can be continuous, which is like a real number. It could be like 82.0179, something like that, a floating point number. So that's numerical data. So categorical data is going to be used for grouping or categorizing our data set. So for example, if we run a clothing store and we have a set of shirts that we sell at our store, we can group them by the color of their shirt. We can group them by red, yellow, and green. And then once we have all the red shirts in this bucket, all the yellow shirts in this bucket, all the green shirts in this bucket, then maybe we want to compare the sales from past year across each color to see which color last year sold the most. That's definitely something that we would care about knowing, because maybe that could indicate that there's a preference for red shirts or a preference for green shirts or yellow, however it may be. And so that's categorical variables. Now, categorical variables are then separated into nominal and ordinal variables. You won't really see this like being talked about, and it's not necessary if you really want to know a lot about statistics, really, especially in this course. But it's nice to know because you will actually distinguish between it when you work with real data. So nominal data is nominal categorical data. It's just literally, it's unordered categories. So like red, yellow, and green have no specific order. They're just going to group and categorize your data. These are nominal categorical data types. Ordinal, on the other hand, is a little bit different. Ordinal categorizes your data, but it has a specific order. For example, when you answer a survey and they ask you if you strongly disagree, you disagree, you're neutral, you agree, or you strongly agree, that is an ordinal categorical variable because there's an order to your level of agreeance with a specific thing. And so that is a little, real quick little tidbit on the difference between nominal and ordinal. And so, yeah, that's everything we have for data types. I want to move into, some other further concepts as well. And so let's head into the next video. So in order to do statistics, we have to know some fundamental concepts of probability. When we talk about the probability of an event occurring, you can literally just think of this as the number of ways that it could possibly happen over or divided by the number of possible outcomes of an experiment, where the number of outcomes is what we call the sample space. Now, the sample space is just all the possible outcomes of an experiment, and a sample space is made up of events. And so an event is a subset of the sample space. The sample space is everything that can happen. An event is a subset of things that can happen, 1 or 2 or 3 things that can happen. So for example, when we flip a fair coin, right, a fair coin has a probability of 0.5 being heads, 0.5 being tails. The sample space, all the different possible outcomes, if you flipped it once, is going to be heads or tails. You can only get heads, you can only get tails, one or the other. That's the entire sample space. When we talk about the event, what's the probability of getting a head? The event there, we can call it event A, is going to be just heads. So heads is just one event in the sample space. Tails is also one event in the sample space. And so we represent probabilities as fractions or decimals between 0 and 1, because a probability has to be between 0 and 1, inclusive of 0 and 1. And so, for example, when we talk about flipping a fair coin, we know that a fair coin has probability 0.5 or 1/2 of being heads, or 0.5 or 1/2 of being tails. So the probability that you flip this coin 3 times, 1, 2, 3, and on each given time you flip it and receive, each given time you flip it, the probability that on each given time you flip it, you receive heads every single time, is going to be the probability of getting heads on one flip raised to the third, which is going to be 0.125. And so I think, since we're talking about probability of an event occurring, why is the probability of the event here, is going to be 3 heads in a row? That's the event. And the sample space is all different possible outcomes of this experiment. And so I think this is a good time to understand, what does it really mean for a probability of an event being the number of possible ways it can happen divided by the total number of outcomes. And so let's head into a handwritten example. All right, so this is what I had written on the previous slide. We had the probability that we flip a coin 3 times in a row and get heads every single time is going to wind up being 0.125. And because on each single coin flip, there's a 0.5 chance that you get a head. And so I wanted to say, we had this other formula that the probability of this right here, okay, is also equal to the number of ways it can happen divided by the number of outcomes, right? Well, the number of outcomes is really just the sample space, right? The number of outcomes. I'm going to scratch out that. We can leave it as is. We know that's just the sample space. So I'm going to write SS. And so what do I mean by, how do I get this right here, and how do I calculate this to be able to get this, to make this formula actually make sense? Well, the number of ways that can happen, we could start by drawing a tree. So a tree where, and I'm going to draw it this way because we're talking about, you think of a coin flipping in the right direction, or at least I do. On the first flip, right, we know that we can get a head on this, and we can also get a tail, right? So this right here is going to be flip number 1. So flip number 1. And we know that if, let's just say on the first flip, we got a head. Well, on the second flip, we know we can either get a head, right, or a tail. And I'm going to give myself a little bit more space. And get a head or a tail. So it's a head or a tail. We know that on the second flip, if on the first flip we got a tail right here, then that means on the second flip we can get a head. or a tail. And this whole section right here is going to be our second flip. And then we know on the third one we could either get a head or a tail, a head or a tail, and then the same thing here, a head or a tail, a head or a tail. And this whole entire column right here is the third flip. Now if you look at this, right, this one little trajectory right here is us flipping heads on the first flip, heads on the second flip, heads on the third flip. And if you can see that this little outcome right here, I'm gonna draw it again actually. This outcome only happens 1 out of 8 different times. There's only 8 of these different paths. There's this one, and then you could also branch off, and so you got heads, and then tails. This is one of them. This right here is another one. You can get tails, and tails. You know, you can get, not to get this too messy, but you can get tails, and then you can get heads, and then you can get heads again, right? This is one little possible trajectory. And so there's right here 1, 2, 3, 4, 5, 6, 7, 8 possible trajectories. And the heads sequence is only one of those, right? So it's this one right here accounts for 1 out of the 8 possible trajectories. And this is exactly what we wanted to test the probability of. And so the number of ways that heads can even happen is only one, right? Because there's only one possible trajectory here in this tree. And the number of ways, the number of outcomes of the entire experiment across all different possible, these are all different possible trajectories over 3 coin flips. It's going to be the count of all of these possible, these leaf nodes right here, which is 8, and they represent all different possible trajectories, which is all different possible outcomes to this experiment. And so we get 1 over 8, and 1 over 8 is equal to 0.125. And there we have our answer. So in this video, I want to talk about some common statistical measures that we'll need to know. And a lot of times what we're doing is we're either using these statistical measures to describe our data, or we're using it to be able to confirm or reject a hypothesis. And we'll get to that later on. But the first one I want to start with is the mean. It's commonly referred to as the average. It's the one that I believe everyone knows the most. And it's just the sum of the data points or the observations that you have divided by the number of observations. I believe everyone has calculated the mean or the average at some point in time. And so, but it's the most commonly used, and I think it's a good one to start off with, the median. And so the median is going to be the middle of your data set. And the median is the value where at this value, 50% of your data lies below it and 50% lies above it. That's what it means for the median to be the middle of the data set. And we commonly use the median as a measure of what we call central tendency. It's just the center. You know, the mean and median are supposed to give us a center, but the median is a better measure of central tendency, or the center of our distribution of our data, when we have a skewed distribution, when it's not a perfect bell curve. You may have heard of the bell curve. But a percentile. So a percentile is where, if I say I have, for example, the 25th percentile, if I say that, this is a value, like a number. It could be any number. It just depends on the distribution that you're working with. It could be 2.75, whatever it is. It's the value where 25% of the data falls below it. Or you could also say 75% of the data falls above it. And so that's a percentile. The median is, since 50% of the data lies below the median and 50% above it, the median is going to give us the 50th percentile of our data set. Variance is a measure of variability. It's going to tell us in this formula right here, we'll see that, you know, variance is commonly represented as sigma squared. It's just going to be the sum over all of your data points subtracted off from the mean. So we're going to calculate the difference between every data point you have and the mean of the data set or the observations squared. And then we're going to divide it by the number of observations. And sometimes you'll see it divided by n-1, but that's besides the point here. But essentially what it's doing is it's just calculating the variability or the deviation of each data point from its mean. And that's a way for us to measure the dispersion or the variability of our data. And moving on to standard deviation. The standard deviation is just the square root of the variance. And so they all have their own use cases. The variance and standard deviation, a common use case of it is measuring volatility of a stock. And so standard deviation and variance will be used to measure the volatility of a stock, how much it deviates around its mean. And so, yeah, I think let's head into a really quick, very simple, concrete example so that we can see these be applied in action. And so I have in front of you a list of observations, and I've said that they're x, right? I've set it as a variable x, but that's besides the point. These are a list of observations, and so I got maybe I did some experiment like I rolled a die or something like that. But this is all I have. This is all the data I have. I don't know this is a die. All I know is that I ran an experiment and I did 1, 2, 3, 4, 5, 6, 7, 8, 9 trials of it. I collected 9 observations, and this is what I got. So how do we let's first start off by calculating the mean, right? If we think about this, we have the mean is going to be, we can commonly represent this as mu, but in our case, we're going to represent it as x bar, right? And why do we do that? You'll see in inferential statistics the difference matters, but the mu is going to be the population at large. Mu would be if we had ran this experiment not 9 times, but an infinite number of times, like if we knew it was a die, right? But x bar is a sample because all we have is 9 observations here. And so this is what the mean is going to be. It's going to be the sum of all of these, and I'm going to group them by like so that we can make this fast. 2 plus 4, okay, plus 6, plus 4, plus 5, plus 6. And so it's going to be 6, 12, 16, 21, and then 27. And remember, we divide by the number of observations, which is 9, and that's going to give us 3. So the mean here is 3. Now, if we think about the median, right? So let's move on to the median. So and I'm going to first write this here. The median is going to be, I'll write that a little bit clearer. The median is going to be, if we had, now, first things, if you want to calculate the median of a data set, computers usually do this, but what you do is you sort it. If you remember, you're supposed to sort it in ascending order, and then you find the middle of it. And a common trick is just to start at the leftmost item right here, the leftmost observation, cross it out, and then cross this one out. Cross this one out, cross this one out, cross this out, and so on, until eventually what happens is that you get down to 1 item or 2 items. And if you get down to, if on your last right stroke you get down to 2 items, you need to take the average of them. And if you get down to 1 item like we have here, you just use that item right there. And so the median here is going to be 3. And luckily enough for us, the median and the mean are exactly the same. And so now let's think about the variance. And so the variance, remember, follows a formula where we take each observation, we subtract off the mean, and we sum that all up, and then we divide it by n. And so this is going to be, we're going to start with the 1s here. It's going to be 1 minus 3 squared plus 1 minus 3 squared, because 3 is the mean and 1 are these 2 observations. These are the 2 observations, or 1s. And then we're going to do 2 minus 3 squared plus 2 minus 3 squared. And then we get to these 3s. And now 3 minus 3 squared, right, is just 0. So we don't really need to write those out. And so we can just replace these 2 right here, which is 0. Cool. And then let's continue, and I'm going to continue down here. 4 minus 3 squared plus 5 minus 3 squared plus 6 minus 3 squared. And, you know, this one right here, and I'm going to, since we have everything down, I don't have to keep that list up. That should be good. This is all going to turn into 1 minus 3 squared right here. That's negative 2 squared. That's going to be 4. And so all these are going to be positive numbers. This is going to be 4 as well. Plus 1, 1, because 2 minus 3 is negative 1 squared is 1. So 1, 1, plus 1. And then plus 4 minus 3 squared is 1, 2. 5 minus 3 squared is 2 squared, which is 4. 6 minus 3 squared is 3 squared, which is 9. And then if you add this all up, you get 8, 10, 11, 15, and then 9, which is 24. And so you have 24. And remember, you have to divide by n, which is 9. It's the number of observations. And then so we have 24 over 9. This is going to simplify to 8 over 3. And this is our variance. Remember, this is our sigma squared. And so our standard deviation, just to drive this home, sigma, commonly write standard dev. If you use Excel, you'll see it written that way as well. It's just the square root of 8 over 3. And so that's how you calculate the variance. That's how you calculate the median and the mean. And given some observations right here, we had n is equal to 9 right here. So we had 9 observations. We just collected some samples, and then we calculated the mean, median, and the variance, and the standard deviation of it. So I want to talk briefly about 2 different ways to determine the shape of a probability distribution, assuming that you are comfortable with what a probability distribution is. If not, we have a course on probability that goes through what different probability distributions look like, discrete and continuous. So please review if you're not well versed in that. But moving on with the lecture, skewness is one measure that we like to know about a probability distribution. We want to know if it's skewed or not. Kurtosis is another one, and we care about these because when we get into deeper analytics and statistics, we're going to care about whether we can assume that our data is normally distributed or that our data is a bell curve. And so if our data is not normally distributed, a lot of the assumptions that we make when we do hypothesis tests, etc., they fall, and we can't use them. And so it's very important for us to be able to assume that our data is normal, or to be able to not assume that it's normal. And so skewness is the first measure that we care about here. And so skewness is going to tell us whether our distribution is symmetric or not. If our distribution is skewed, then it's not symmetric, it's asymmetric. And so if, for example, on this picture over here, a left skewed distribution or a negative skewness is going to be that the tail of this distribution, the long tail, is going to be on the left side. So think about left skew means long tail on left side. And right skew is going to mean that the long tail is on the right side. And this is called the positive skew. And so the skewness of a distribution affects the measures that we have on it. And so that's kind of why we care about whether it's a distribution is normally distributed or not, because it's going to affect whether we can use the mean or we should use the median, etc. But you can see that for a left skew distribution, the mean gets dragged to the left quite far away from the highest peak, where in the bell curve, the mean is the peak right there. The median gets dragged a little bit, but not that much. And it kind of holds its ground. I like to think of it that way. It holds its ground a little bit better. The mode is the most frequent value in a data set, if you can remember that. And so it's always going to be at the peak of the distribution. And so the mode is always at the peak because this is the point where the highest probability value is. And the same thing for the right skew, right? The mean gets dragged to the right, the median gets dragged not as much as the mean, and the mode still stays at the center because it measures the most frequent value, and the most frequent value has the highest probability under this distribution. And so skewness is one way to determine if a distribution is symmetric or not. Kurtosis is another way to kind of characterize the shape of the distribution, right? Not only does a bell curve need to be symmetric about its mean, but it needs to have a certain shape to it. And what I mean by that is that kurtosis is going to measure the sharpness of the peak in our distribution, or the heaviness of the tails of the distribution, how much probability density is under our tails. And so, for example, in this picture that I have on the bottom right, the distribution with the sharpest peak is going to be this red one right here. And this one is going to have the highest kurtosis, and the kurtosis is going to go down with each one of these. And so that's what it means to have high or low kurtosis. and it measures the sharpness of this peak. And so these two things really characterize whether something's a normal distribution or not. The perfect bell curve, it may look kind of like this black distribution, if you can see that right there, or maybe even the green. The green of the black is pretty close, but it has a certain kurtosis to it, right? If the peak of this distribution that we have is too sharp and it's skewed, it's definitely not normal. If it has normal kurtosis, but it's still skewed, it's not normal. And so these two measures really tell us a lot about how normally distributed our data is, or how not normally distributed our data is. And we can measure them. Just like we can measure variance of a distribution, we can measure its skewness, we can measure its kurtosis. And these two measures are known as the third and fourth moment, respectively. Skewness is the third moment of our distribution. The kurtosis is the fourth moment of our distribution. And moments are just statistical measures on a distribution. And you can look them up online. Their formulas are very similar to how we calculate variance. And so if you've calculated variance, you can do this. You can do skewness and kurtosis. And you can also determine this by visualizing this. You can calculate it using the coefficients and the formulas, but you can also plot this, right? You could plot these, you could plot your distribution and say, all right, that's skewed. You could plot it and say it's got pretty high kurtosis, it's not normally distributed, or it has really low kurtosis, like this purple box right here, which is practically the uniform distribution. And so you can visualize your data and be able to determine these characteristics without doing, closed form calculations. And so that's what we're going to move in the next video. What are some common visualizations of our data, like the box plot here, or a histogram that allows us to be able to tell a lot of these characteristics of our, the distribution of our data without doing hardcore calculations. So in this video, I want to go through plotting some data to show that when you visualize it, you can actually tell if it's symmetric or not, and to determine its shape, so that you don't have to do a closed form solution every time. And so I'm using RStudio. You can download RStudio from the CRAN website. That's C-R-A-N. You can download the software there. And we're using ggplot2, which is a package within RStudio in the R programming language for plotting and visualization. And so if this is the first time you're using ggplot2, or you just installed RStudio, you can install the packages for ggplot2 using this command up here. You would just uncomment that and run that command in your terminal. And so first, I want to plot a normal distribution. I want to start off with histograms because they are the most popular. And so this is going to plot a normal distribution. And so as you can see, if this was our actual data, I just simulated a sequence of 100 numbers and assumed they were normal using this built-in function dnorm and R. As you can see, if this was our data, we could safely assume that it's symmetric. I mean, it's centered around 0. It looks perfectly symmetric and normal. And I think you'd be well within your rights to go ahead and assume that this is a normally distributed data set. On the other hand, I want to plot some skewed data sets. And so let's go ahead and plot a left skewed and a right skewed data set. So all of this code is going to do this for me. I'm assuming I'm using, instead of a normal distribution for the symmetric one, I'm using a beta distribution, which is a different type of distribution. And so as you can see, this one has a left skew because the tail is on the left side, and this one has a right skew because the tail is on the right side. And if this was your data and you had plotted it, everyone would look at this and say, this is skewed, this is not normal, we can't assume normality, and you would be perfectly right to do so. But in a lot of cases it's like this, but in some cases in the real world, what you're dealing with is data that is shaped kind of odd, and you can't really assume just off visualizing that it is actually normal or skewed enough to where you can't use a specific test or assume a certain thing. But in these cases you can. So that's histograms. So now let's move into box plots. So I've already plotted this, but this code right here is going to be able to generate this plot that you see on the right. And how we could read a box plot is that this bottom, like this is a box and whisker plot. This bottom whisker, this point right here on these box plots, is going to be the minimum value in the range of values that the histogram takes. This right here, this line, is going to be the first quartile or the 25th percentile of the distribution. The middle right here is going to be the median. This one right here is going to be the 3rd quartile or the 75th percentile. This point is going to be the max, and then these little dots are outliers in the data set. And as you can see on this left skewed distribution, the box is closer to the maximum point, so because the distribution's leaning that way. And on the normal distribution, the box is in the center because it's symmetric. And on the right skewed distribution, you can see that the box is leaning towards the minimum value, which would be on the left. If you're thinking about like visualizing the histogram, it would be on the left. And that is how you can tell in a box plot if your distribution of your data is skewed based on just plotting it. Box plots and histograms are the best ways, I think, to explore your data and determine its distribution so that you can be safe or at least gain some intuition around whether you can assume normality. So now we're going to delve into inferential statistics. So in inferential statistics, our goal is to use inferential statistical methods to draw conclusions about a population given a sample of data. And so that's the goal of inferential statistics, is that we have this small random sample, like if you see over here in this picture, in this diagram, we have a small random sample that we've collected of observations, and we want to use the statistics that we compute, whether it's the mean, the median, the variance, etc., on this sample to be able to say something about all of these observations in the population. And you can imagine that our sample could be really small compared to the population. So these methods are incredibly powerful. Now, in the world of big data, this isn't as much a need as it was beforehand when we didn't have so much data, so we only had a few observations, but it's still used widely, and so it's still an important thing to know about. And so the thing is, with inferential statistics, in order for our sample, this little tiny sample we have right here, to be representative of the population at large, for us to use our statistical methods, it needs to be a random sample. So what do I mean by a random sample? Like, why does it need to be a random sample, first off? That was the first thing that's really hard to explain. Well, there's two reasons. One, if we take a random sample, this means that our sample is representative of the population at large. Why is that? Because it means that every observation in the population had an equal chance of being selected and thus represented. And so the best way to understand this is to imagine that we didn't do a random sample. Imagine that we literally picked the observations that were the easiest to get, or the most convenient to get, or we picked them because we liked them for some reason. Well, in that case, not every single observation in the population had an equal chance of being represented, and because of that, we can't honestly say with good faith that our sample is representative of the population at large. And this sort of method of not randomly sampling leads me into my second reason as to why random sampling matters, is that if we don't sample all these observations at random and they don't have an equal chance of being represented, we could be inducing unforeseen bias, or maybe not even unforeseen, maybe just straight up bias. And the thing is that even though you would think, okay, well, what if we just controlled across several characteristics? What if we made sure that our sample, right, matched the population's characteristics across several characteristics: gender, height, age, occupation? We made sure it was as close to being the same as the population as possible. Why can't we do that? Why can't we just take the sample and make sure they match the population? Well, the thing is that you can do that, and then you'll actually see that done a lot in statistics, but it's usually done by professionals that have a lot of domain knowledge. The thing is that when you do that, there could be unknown characteristics that you're not controlling for. We're human beings. We can't think of everything. We don't know everything. And for that reason, there could be characteristics that don't match, that are in your sample, that distribution across those characteristics that we don't know, it could not match the population. And so that's another reason. We want to make sure our sample is representative. We want to make sure it doesn't have high bias. And moving on from that, so there's a couple of key concepts to make inferential statistics work. One is the Central Limit Theorem. The next one is based off the Central Limit Theorem. We're going to get into testing hypotheses. And then in order to test a hypothesis, we need to know this idea of statistical significance and a p-value. And then from there, we want to be able to construct confidence intervals for the measurements that we have. So let's hop into breaking down these concepts and truly understanding them. So in this video, I want to talk about the Central Limit Theorem. The Central Limit Theorem is fundamental for our understanding of statistics. It allows us to be able to test hypotheses. Without it, we couldn't do it. And so what does it state? Quite simply, it states that if we were to have a population of data and we were to take repeated random samples from that population, and then for each of our random samples, if we had calculated the mean of each one of those samples, and then plotted the distribution or the histogram of all of those sample means, that distribution would be called the sampling distribution, and its mean, the distribution of all sample means, its mean would be equal to the true population mean, and its standard deviation, which is called the standard error, would be equal to the true population standard deviation divided by the square root of n. That's assuming that we took random samples that were all of the same size, and typically we want them to be greater than size 30, and we took an infinite number of them, right? If we take less than an infinite number, then we're not going to have the mean of our sampling distribution be exactly the same as the population. The standard deviation is not going to be, the standard error of our distribution, our sampling distribution, is not going to be exactly equal to the population standard deviation divided by the square root of n, but it will be approximately equal to that. And not only that, our sampling distribution will be nearly normally distributed. And so this is quite powerful, because now when we take a random sample from a population, we can compute certain statistics on it, because we know this fundamental theorem about the sampling distribution and how it would pan out if we took an infinite number of these. It's going to become really important when we start doing t-test or other hypothesis tests. And so this is how you compute the standard error. Let's hop into a quick visual example to make sure we have a good understanding of how this sort of pans out. And then we're also going to see a simulation of this in R. Let's assume that we have a population. And I'm going to draw this box. And this box is going to be our population. And it's got a bunch of different observations in here. Okay. And what I'm saying is that the Central Limit Theorem says that if we took a random sample, say we took this sample right here, and let's just say it's of size 30, just to keep things simple, and then we took its mean, and so I'm going to say mean of 1, right, because this is sample 1. If we took its mean, all right, right here, and then we took, let's say, another sample, all right, of size n equal to 30, and this is S2, and we calculated its mean, say mean 2, and then we continue that literally up into S is equal to S infinity, where we calculated the mean of this one as well as mean infinity. And I'm going to draw our little sample. And then we took each of these means that we calculated, these sample means, and we plotted a distribution of them. Ooh, can be better than that. That will cut it. And we plotted the distribution of them. The distribution will be nearly normal. Okay. It will have mean equal to the population mean. So that means this right here is equal to mu, which is the population mean. Mu is the population mean. And then X bar is what we commonly refer to as the sample mean. And then we're also going to say that its standard error, which is the standard deviation of this distribution, is going to be equal to the true population standard deviation, which is sigma, divided by the square root of our sample size. And so all these samples right here, if they were n equal to 30, if they were all of size 30, then it's going to be the square root of 30. And the sigma is just the standard deviation of all of these, all the observations in your population. And so that's what the Central Limit Theorem states, that this really does happen. And so as long as we meet some criteria. And the thing is that the distribution of your population does not have to be normal. Like if we plotted all these observations and they wound up being normally distributed, of course our sampling distribution would then be normally distributed. But that doesn't have to be the case. Our population can be incredibly skewed. It could be right skewed, right? And then if we took repeated random samples like this and calculated their means, and let's just say that this is the mean right here, our sampling distribution would be nearly normal still and have mean equal to the true population mean, and its standard error equal to sigma over the square root of n. And that's a really powerful statement, because every sample that we take, we can now calculate what's the probability of obtaining that, given that we assumed a particular population mean. And so that's a little bit further than where we are at right now. We're going to wait to explain that in a different video, but let's simulate this in R. So here I am in RStudio. I'm using the ggplot2 package to build this histogram that you see right here. And I'm setting a seed, so if you set the seed and you copy this code right here, then you'll be able to get exactly what I get. And so I'm going to run this just to show you how I did it. I press Control Enter, that's how I run it. And what I'm doing right here is that I'm setting the population mean to be 100. I'm setting its standard deviation to be 15. I'm setting the size of our population, in this case it's just 10,000, so we can make it fast. And I'm simulating from a normal distribution all of these. So I'm saying, what I'm telling R right here is give me 10,000 observations that come from a distribution that has mean equal to 100 and standard deviation equal to 15. And then I'm going to take 1,000 random samples of size 20 from this population. So each one is of size 20. And then what I do is this line right here is going to go through each one of these. So what it's going to do is it's going to take a sample from the population of size 20. This is what this does right here. So it's going to take that sample. It's going to calculate the mean of this sample, right here. And then it's going to do that num samples times, which is 1,000 times. And this replicate is just making sure that it does it again and again and again and again. And then this code actually generates the distribution, the sampling distribution. Now, to verify something, this sampling distribution, right, I said that it should have a mean. It's mean, so like the sample distribution, I'm going to say sample distribution, its mean is the sample means, and that should be approximately equal, because we're simulating here, to the population mean, which we know is 100. And so if I print sample dist, which should be sample dist mean, it's 99.96, which is really close to 100. It's practically 100. And I also said that its standard error, right? Its standard error standard error should be equal to the population standard deviation divided by the square root of n. Well, let's see what its standard error is. It's 3.3755. Well, this should be equal to the population standard deviation, which is 15, divided by the square root of our sample size. And we get 3.35. And so those are really close to each other. And if we were to increase the number of samples, maybe to 10,000, we would see that this thing would closely approximate the mean of the population, and the standard deviation, the standard error would be equal to the standard deviation divided by the square root of n. And so I wanted you to see that it actually does work. And feel free to play with this or expand your knowledge. But it's a useful thing to understand when you go to understand statistics. So in this video, I want to talk about hypothesis testing. So hypothesis testing is a way for us to be able to take our sample that we have, a random sample, and be able to test whether a hypothesis about the population is true or false, just based off some statistic that we calculated on this sample. It could be the mean or the median or something else. And so commonly in hypothesis testing, this is how it is structured. We have a null hypothesis, right? So a null hypothesis can be something like the mean of the population in terms of height is 170 centimeters. And you have a sample, right? And you take a sample of people, and then you calculate the average height of that sample, and you're trying to test this null hypothesis that the mean is actually 170 centimeters. And so that is the null. The null is like, hey, the mean of this population in terms of height is 170 centimeters. The alternative hypothesis could be something like the mean height of the population is greater than 170 centimeters. And so you're going to take the null, which says 170. You're going to take the alternative, which says it's greater than 170. You're going to have your sample, which you calculated its mean. And then using a hypothesis test, you're going to figure out, hey, is the mean of our sample, is it far enough away from 170 centimeters for us to be able to reject the null hypothesis and say, I can't say that's 170. Now, I must say that the alternative is what I have to favor myself towards. So that's how you can think about a hypothesis test. How do we determine if we should reject the null hypothesis? Well, the p-value is something that we calculate to determine the probability of observing our statistic, or our mean of our sample in this case, a probability of observing it or a more extreme outcome given that our null hypothesis is true. So we're just going to assume that our null hypothesis is true, and we're going to say, no, this is the case, it's 170 centimeters. We're going to calculate our mean of our sample, and if it differs enough, if the probability of us observing the mean from our sample is so low and past a certain significance level, we're going to reject the null in favor of the alternative, which says it's greater than 170 or it's less than 170, depending upon how we structured it. And so this gets us into two types of errors that can happen with this. One, right, we can actually reject the null when the null is actually true. It's possible for us to reject the null, saying that it's greater than 170 centimeters when it's actually true. And so in a court of law, you can think of this as in a court of law. Traditionally, how it is that a defendant, a person that's on trial, they're assumed to be not guilty. So that is going to be the null hypothesis, that this person is not guilty. But let's just say that we find some evidence against them, and then we find them to be guilty. The alternative is that they're guilty. Well, that means we just rejected the null. But what if it is that they're actually not guilty? If we find a person guilty but they're not guilty, then we just rejected the null when the null is true, which would be terrible. Type 2 error is we're failing to reject the null when the null is actually false. So let's assume our person is actually guilty and we don't find enough evidence against them, which is not good. And we find them not guilty. We fail to find them guilty. And in that case, that's a type 2 error. So let's hop off this slide and let's move into a visual example to really understand what I mean by a p-value and the significance level, and tie this back into a sampling distribution. And so let's actually run with our example that we explained in the slides, right? Let's imagine that we are calculating the mean of the population. We want to test the mean of the population, the mean height. Let's do mean height. And so what we do is we know that we take a sample. We take a sample from this population. So here's our sample. There's our sample. And then we calculate the average height here. And let's just say that the average height that we get here, the mean height here, is equal to 158 centimeters. And let's imagine that, I don't know, maybe it's just well known about this population that the average height is actually 170 centimeters, right? And what we want to say is, okay, let's just figure out if this is actually true. So our alternative hypothesis is going to be that it's not equal to 170 centimeters. We're going to say, okay, the null hypothesis is what's been known for however long. It's 170 centimeters. It's the average height of this population. And our alternative is just going to be that it's not equal, right? So, and what we do is we take the sample and we calculate its mean height, which is 158 centimeters. And then we go, okay, so we're assuming that the null is true. And if the null is true, then we know that based on the Central Limit Theorem, that the sampling distribution, if we took repeated random samples of this size, the sampling distribution would be nearly normal, right? Its mean would be centered at the true population mean, which we're assuming is 170 here. We're just running with this and assuming it's true. And we know that its standard error, or its standard deviation, would be equal to the population standard deviation divided by the square root of our sample size. But we don't have the population standard deviation for the most part, and so we just use the sample standard deviation. You'll see that happening. It's a tiny detail, but mostly we'll just use the sample standard deviation. And so using the sample standard deviation, or the standard error, calculating the standard error, and assuming that the mean is equal to the true population mean, we can build this hypothetical sampling distribution. And we can assume that this sample comes from this distribution. And let's just say we got 158, and let's just say that we look at 158, we say, okay, 158 is over here. And then we calculate this area under the curve right here. Now this area under the curve is the probability of us getting a value that is less than 158, as or less than 158. And this right here is called our p-value. And let's just say that our p-value here winds up being 0.02. Now, the thing is that beforehand, if this was a common hypothesis test, is that we would establish some significance levels, right? And since we only really care about testing whether it's not equal to 170, we're going to say, okay, if the mean that we get is far enough to the left, right, if it's past this significance threshold on the left, or if it's far enough to the right, like over here, if it's far enough, we're just going to say it's definitely not equal to 170. And so in our case, it was far enough to the left, and it was far enough less than 170 to where it went past our significance threshold, which could have been like 0.025. And we finally said, okay, this is extremely unlikely for me to be able to get this sort of mean, this average mean, assuming this sampling distribution. It's way past my significance level. And so what I'm going to do is I'm going to reject the null in favor of the alternative. And that is how hypothesis testing actually works. So we've talked about hypothesis testing. We've talked about, the Central Limit Theorem, what a sampling distribution is, how we can assume that our sample mean comes from that sampling distribution. We've talked about p-values and what it means to reject or fail to reject a hypothesis. Now, we have a decent understanding of what it means to take a sample and compute some statistics and run some tests and say something intelligent about the population at large from just a really tiny random sample. And so we're primed right now to talk about confidence intervals. So what is a confidence interval? A confidence interval is a range of values such that we can have a certain level of confidence that the true value of a population parameter, aka the mean, or as it could be known as the mean, falls within that range of values. And so what this we commonly use 95% confidence intervals. So if we take a sample mean and we construct a 95% confidence interval around that mean, a range of values, we can say that we're 95% confident that the true value of the population mean falls within this range. And that interpretation is quite decent. I think it's decent. But it's also an oversimplification of what the confidence interval really means. What it really means is that if we had, for example, taken a random sample of 30 people from the population, calculated their average height or their sample mean, constructed a 95% confidence interval around that mean, what the real interpretation of that 95% confidence interval is that if we had taken another sample of 30 people, constructed a confidence interval the same way, taken another sample and constructed a confidence interval, and did that an infinite number of times, the true population parameter would fall into 95% of those confidence intervals that we constructed from all of those infinite number of samples. And that is the actual interpretation of it. But that's not as you don't see it commonly used, because that's actually really hard to explain to like a client or a person like a business professional or someone on your team, etc. And so we just say it's 95% confident that it's within this range. And so this right here is how you actually compute the confidence interval. X bar is our sample mean. It could be our average height of our sample. And then we do a plus or minus, right? We're going to add to it this number right here, this value right here, z times the standard error. We're going to go this far out to the right, and then we're going to go that far out to the left by subtracting. So z is a z-score, and we use a t-score or a t-statistic as well. This is a z-statistic, but we can use a t-statistic, and we'll talk about that later. But a z-statistic is going to be able to it tells us how far away from the mean, how many standard deviations away from the mean we have to go under a normal distribution to produce a confidence level. So a z-score of 1.96 is going to get us 1.96 standard deviations away from the mean to the right and to the left. And then if you imagine the area under the curve, the area under the distribution between those between the z 1.96 to the right and 1.96 to the left, that is going to be 95% of the density in a normal distribution. So that's how you construct the interval. I think that was a lot. Let's move into a visual example showing how this actually works. So let's first talk about, this confidence interval. I'm going to start with our population. It's a little bit smaller than beforehand, but we have this population here. And we take our sample, we draw it out, this is our sample, and then we calculate its sample mean, which we can now represent as x bar. And what we know is that this sample mean right here, it comes from a sampling distribution, right? Where the sampling distribution is nearly normal. I can draw a better normal distribution. It's a bell curve, nearly normal, with mean equal to the true population mean, and standard deviation that is equal to, we're going to use the sample standard deviation because we said we can do that, and it's happened a lot, it's used a lot, divided by the square root of our sample size, n, right? And that's going to be our standard deviation. Now, what we're going to say is that now we want to construct a confidence interval. So let's just say that our mean is like somewhere over here, okay? What we're going to do is that this is our mean. This is where our mean right here landed. We're going to assume that it comes from the sampling distribution. And if it comes from the sampling distribution, then we know that we can assume it's normally distributed. And in a normal distribution, if we wanted to find the point where, say it's a normal distribution, if we wanted to find the point where 95% of the density of the area under the curve is, what we can do is we can go 1.96 standard deviations to the left, and then 1.96 standard deviations to the right, and then this area under this curve, right, would be 95% of all of the area under the curve. And so since it comes from the sampling distribution, and since the sampling distribution is nearly normal, and since we know that we can step 1.96 standard deviations to the left and 1.96 standard deviations to the right to construct an interval under a normal distribution that has 95% of its density right there, we can use the Z-statistic, which is going to give us that standard deviation of 1.96. Right? And so what we can do is then construct an interval around it, right? That's, 1.96 times the standard error, because the standard deviation of the sampling distribution is the standard error. And then we can use it over here to construct 1.96, a positive 1.96 times the standard error. Okay? And so now here's the thing, right? Is that if we did take this sample mean right here and constructed this confidence interval, right, that you see in front of us, the true population mean did wind up in it. But it's not always going to be the case. If you took repeated random samples, right, if you took another one here, another one here, another one here, and so on, one of these may wind up over here, just quite unluckily. And then when you constructed a confidence interval around it, right, the sample mean might not be within it. So it might not be the case. It could be the case that this sample mean did come from this distribution, and we're going to assume that, but it's not always going to be the case that you're going to construct a 95% confidence interval and the population mean is going to fall within it. So what we say is that what we do is we say, okay, this is the correct interpretation, that if we had taken a random sample, right, of the particular size that we had, and we had constructed a 95% confidence interval, right, using that sample mean, and then we took another one, okay, and constructed another 95% confidence interval, and then we took another, right, and then we constructed another 95% confidence interval, and we took another all the way up into infinity, and we constructed another 95% confidence interval. We're saying that in 95% of these cases, the true population mean is actually going to lie within the interval. And so let's just say that this is the true population mean. if we kept on like just doing, grabbing samples, computing their means, constructing confidence intervals, grab another sample, compute the mean, construct another confidence interval, and just kept on going all the way up into, infinity, the true population mean would not change. But what we can say is that doing it this way, that 95% of these intervals, like this one was that had the mean within it, 95% of these intervals would contain the true population mean. You see that these three here in our example did, and this one right here did not. And so that's what it means to construct a confidence interval. We're going to say that if we kept on taking samples of this size, constructing confidence intervals this way, that 95% of those confidence intervals would contain the true population mean this way. And that is the correct interpretation of a confidence interval. We've talked briefly about hypothesis testing, what a confidence interval is. Hopefully we're now comfortable with what a sampling distribution is. And now we're bridging into how do we actually go about doing or conducting a hypothesis test. And now that we're bridging from these theoretical concepts into actually conducting a test, I want to explain the difference between using a Z-statistic and a T-statistic. And so just to recap, we now understand that under the Central Limit Theorem, the distribution of sample means, because we're using the mean in this case, this distribution of sample means will be nearly normally distributed, have mean equal to the true population mean, and a standard deviation or a standard error equal to the standard deviation of the population divided by the square root of the sample size. We even simulated that in R. And so the thing is that, and also not to mention the Central Limit Theorem likes for us to have sample sizes greater than 30 for it to hold. And so the thing is that in the real world, chances are we may have a sufficiently sized sample, but we don't know the true population standard deviation. That's not known to us, or the population variance or standard deviation is not known. But when it is known, right? When it is known, we can use the Z-statistic. And so the Z-statistic is used when the Central Limit Theorem holds through and through. When we have a sample size greater than 30, the population standard deviation is known. And if those two things hold, we're good to go to use the Z-statistic. And now the thing is that the Z-statistic is going to take our sample mean, our X bar. It's going to subtract off the null mean, the null hypothesis, the mean of the population that we're trying to test, divided by the standard error of the sampling distribution to see how many standard deviations off of the mean of the sampling distribution we fall. And so we visualized that in the previous example, and so hopefully you remember that. And so that's what the Z-statistic is going to tell us. It's going to be a value or a score, it's commonly referred to as a score, that tells us how many standard deviations off of the hypothesized mean of the sampling distribution we have fallen with our current sample mean X bar that we calculated. And then from there, since we have all the information we need to calculate directly the sampling distribution, because we have the population standard deviation, we know and we have the hypothesized mean, we can determine the probability of observing this sample mean that we just tested. And so the Z-statistic is used when we know everything. The T-statistic is what is more commonly known, and the T-statistic is used when we don't know the population variance or standard deviation. Like, we don't really know the variance or the standard deviation of the heights of all people, and we have a small sample size. And so you can see this is more widely used. Now, the difference between the Z-statistic and the T-statistic is that, since we don't have the population standard deviation right here, we're going to use the sample standard deviation. And because we are assuming that the sampling distribution has the sample standard deviation, that may not be true and probably is not true. And because of that, we have a certain degree of uncertainty now in our, in the shape of our sampling distribution that we have to account for. And how do we account for that? Well, we account for it by using the t-distribution. The t-distribution is kind of like the normal distribution, but it has heavier tails. And I'm going to show you what the t-distribution actually means, but this is how you calculate the t-statistic right here. And then, like the z-statistic, what we did really was we calculated the z-statistic, and now we need to calculate the probability that we actually observe that, right? And so how do we calculate that? We're going to see where the z-statistic falls under a standard normal distribution with mean 0 and variance 1. That's what that means. It's called a z-distribution or a standard normal distribution. And then wherever that z-score falls is going to be the area under the curve outside of it is going to be the probability of observing it. And then for the t-statistic, we're going to take that t-statistic that we got, and instead of seeing where it falls under a standard normal distribution to get the probability of observing it, we're going to see where it falls under a t-distribution to understand, to calculate the probability of observing it. And so the t-distribution, the normal distribution is characterized by mu and sigma. The t-distribution is characterized by n-1 degrees of freedom. So it's characterized by degrees of freedom, where the degrees of freedom is the size of our sample minus 1. And the t-distribution has heavier tails, and so it's going to take us, it takes more distance from the mean to be able to reject a null. And that's because we want to account for this uncertainty. And so let's go into a handwritten example so I can explain this in further depth. Okay, so a z-statistic. And so first, this is what the z-statistic is. We're gonna get our sample. We're gonna calculate its sample mean. We're gonna subtract off the hypothesized mean, or the null hypothesis mean. And then we're going to divide by this population standard deviation over the square root of n, our sample size. And this is our z-statistic. And so once we have this, right, we need to be able to calculate what is the probability of observing a z-statistic of this size. And so the z-statistic, just to note, is usually somewhere between -3 and 3. That's usually where your z-statistic falls, but in practice you can see z-statistics and t-statistics really high. It can be -20. There really is no limit to the size of it, but you'll normally see them between -3 and 3. But once we have the z-statistic, we have this value, what we do is we're going to see where it falls under a standard normal distribution. And so for the z-statistic, just remember we use the standard normal, and the standard normal has a mean equal to 0 and a standard deviation equal to 1. And so let's just say, remember, we're trying to get the probability of observing a z-statistic of this size or extreme. So let's just say that the z-statistic that we have, let's just say it's -2.5. Let's say that. Well, -2.5 is actually going to fall somewhere around here, right? Because 0 is here, so this would be negative, this would be positive. And so this is going to be -2.5. Well, if that's the case, the probability of observing -2.5 under a standard normal distribution or something more extreme is going to be the area under the curve at and to the left of -2.5, extending out into infinity. And so this area right here is the probability of getting z less than -2.5. And so sometimes we care not only about getting the probability that z is less than -2.5, but also the probability that z is greater than 2.5 on the other side. And so 2.5 would be probably about right here. You know, it's not perfect, but I'm sure you get the picture. And the area under this curve right here would be the probability of getting z greater than 2.5. And whether we want one or the other or both just really depends on the alternative hypothesis. If our null hypothesis says that a mean is equal to some number, we could have our alternative hypothesis being that the true population mean is not equal to, you know, that number, fill it in, is not equal to the null, right? It can be that we say that our true population mean is actually less than the null. We could say that our true population mean is greater than the null. And depending upon which one of these alternative hypotheses we choose, it's gonna matter whether we care about this side or we care about this area or we care about both of them. And so for this first one right here, for mu not equal to the null, we're just gonna say, look, what we're gonna do is we're gonna care about the chance of getting a value this extreme to the left of it, so we're going to care about this one, and then we're going to care about getting a value this extreme and to the right of it. We're just trying to see, is it equal to the null or not? And we don't really care if it's less than or greater than. We're just saying, is it so extreme and so different from the null, either to the left or to the right, to where we are forced to reject? Given that we've already elicited some significance level, but we're not going to worry about that right now. And so that's for the not equal to the null. And this right here is called a two-tail, right? A two-tail hypothesis test. And that makes sense because we included both tails. And then for these, for less than the null, we're going to care about just this one. And this is a one-tail. And then for the greater than the null, we're only going to care about this one. And that's for a one-tail. And so that's a little side bit that's going to apply not only for the Z-test or Z-statistic, but also for the T-statistic. And so that's the Z-statistic. We know the population standard deviation, and we use a standard normal to evaluate its the probability of getting it or a more extreme value, and depending upon which hypothesis test we were conducting, we're going to care about whether the left, the right, or both tails. The T-statistic is a little bit different. And so the T-statistic, we still take our sample mean, we still subtract off the null mean, or the hypothesized mean, but we divide by the sample standard deviation. So we calculate the standard deviation of our sample, and then we divide by the sample divided by the square root of n. And so right here, we're using the sample standard deviation to estimate the standard error of the sampling distribution, which we know for a fact, if we are abiding by the Central Limit Theorem, that it's this population standard deviation divided by the square root of n. It's probably not this, but this is our best guess using the sample standard deviation. And so since we're guessing in a way, we have to account for that uncertainty by using not a standard normal, but something like a T, it's called a T-distribution. And so we take our T-statistic and we see where it falls under a T-distribution. Now a T-distribution also is centered at 0, but instead of it having a mean and sigma, right, being characterized by that, those two things parameterizing it and making its shape, is characterized by degrees of freedom, which is equal to the sample size minus 1. And so when degrees of freedom, when the sample size is really small, this distribution has really heavy tails. So it's actually very likely to get to see very extreme outcomes. So like the number -4 may fall over here, right? And you may still see some area under this curve. But -4 under a standard normal distribution would practically have nothing under it. And it would be a very unlikely number to see. And so how that accounts for uncertainty is that our x bar has to be further, if we're using a T-distribution, our x bar has to be further away from our hypothesized mean in order for us to have the same level of significance under a standard normal. For example, this 2.5 over here had this amount of area. A 2.5 over here might have way more area. 2.5, a -2.5 may have a ton of area. And so it may be really likely. And so the probability of observing it or a more extreme outcome may be actually so likely that we can't really reject the null. We can't honestly say that the null is wrong or anything like that. We can't say it. Can't be confident in it at least. And so that's how the T-distribution, that's why the T-distribution is used, because it makes it harder for us to reject the null, because we're accounting for that uncertainty in using the sample standard deviation, and we're also accounting for the uncertainty due to our small sample sizes. Now, one thing to note, as the degrees of freedom increases, as we use larger and larger samples, like say our degrees of freedom here was like 10, but let's just say our degrees of freedom here went up to 100. You would see the degrees of the T-distribution approximate a normal distribution. So as our sample sizes get bigger, our degrees of freedom gets higher, and as our degrees of freedom gets higher, the T-distribution turns into the Z-distribution or the standard normal. And so at that point, we're using such large samples that we elicit our confidence by just making the T-distribution look, be more like a normal distribution. And we're going to get practically the same results as if we had just used a standard normal. All right, so we've learned the difference between a Z-statistic and a T-statistic. And in this video, we're going to talk about how to conduct a T-test. Now, there's a few different types of T-tests, but we're going to talk about two in particular. We're going to talk about a one-sample T-test, which is going to be our first one, and then a two-sample T-test. A one-sample T-test is going to be where we've collected our random sample of data. And remember, a t-test is for when we have a really small sample, particularly less than 30 observations. We have our sample, and we want to test the null hypothesis on that sample. For example, if we have a sample of people and we take the mean of their heights, we want to see if the mean is different than the null mean or the hypothesized mean. And so that's the steps. First, we need to determine what is our null hypothesis. What is our alternative hypothesis? You know, if our null is that the mean height of people in the population is, 165 centimeters, then our alternative hypothesis could be that it's not equal to 165 centimeters. It could be that it's less than or greater than. And then from there, we need to determine a significance threshold. Now we need to then collect our random sample, calculate our sample statistic, which is the mean in our case, and then calculate your t-statistic, which we've already went through there. And then after we have our t-statistic, we know that we can determine the p-value by seeing what is the area under the curve, either to the left either to the left or to the right, or the left and right on both sides. Determine what the area under the curve is, or the probability of observing this statistic or a more extreme statistic under the t-distribution. We saw that in the last video, and that's going to be our p-value. And then once we have our p-value, we need to see, okay, if we know what is the probability of us observing this statistic, this t-statistic, or a more extreme value, if we know that probability, is that probability low enough or lower than our significance threshold so that we can reject the null? Because the significance threshold is going to tell us that, okay, a significance threshold could be, I want there to be a 5% chance of us getting this. If the probability of us getting this statistic or something more extreme is less than 5%, then we're just going to say that the null hypothesis is not true, and we're going to reject it. But if our probability of observing the statistic or more extreme value is greater than 5%, let's say it's 10%, then we're not going to reject the null. So that's a one sample. We literally just take one sample, calculate a statistic, run it through a hypothesis test, right, and see if it differentiates enough from the hypothesized population mean to reject it. So now we talked about a one sample. Let's talk about a two sample t-test, or an independent two sample t-test, the one we're going to talk about. In an independent two sample t-test, that means we have two random samples. We have two groups of observations. Let's just say that group one is a group of people and group two is a group of people. We're going to assume that they're independent, that they're not somehow related. If we're trying to measure the difference in heights or average heights between these two groups, we need to make sure that someone's brother is not in one group and the other brother's in the other group, or they have some family relation or some sort of genetic relation that would make them paired if we're calculating height, and then we don't really want that. We're assuming that they're independent and that group one is not related to group two in any sort of fashion like that. And so the common null hypothesis here is that you have these two groups. So we have two groups of people in our example, and the difference in means between these two groups is 0. And so the null hypothesis is saying that there really is no difference in means between these two groups. And the alternative hypothesis is one of the three that we talked about. Either it's that the means of these two groups is not the difference in means between these two groups is not equal to 0. That means it's either one group is less than the other, or one group is greater than the other, but it's definitely not. They're not the same, right? Or it's like the difference in means is less than 0. So that means one group is significantly less than the other, or the means between the two groups is greater than 0. That means one group is greater than the other, just depending on which group you choose to use as your reference group there. But the test statistic is a little bit different. So we have our two groups, right? We have our two random samples, and we're going to calculate our test statistic by first taking the difference in means between the two groups and then dividing by the square root of the first group's variance divided by its sample size plus the second group's variance divided by its sample size, all under the square root right here. And then that's going to be our test statistic. And now our test statistic is then going to be evaluated under a t-distribution with degrees of freedom as well. And so we're still using the t-distribution to evaluate the test statistic here. And so that's a brief introduction to what a one sample t-test is and a two sample t-test is. And later we'll go through some examples on how to conduct each one. So in this video, I want to go through how to conduct a one sample t-test and then also an independent two sample t-test in R. We're going to do both of them from scratch, and then we're also going to show how to use R's built-in t.test function to do it a whole lot in a whole lot simpler fashion. And so let's start off with the one sample t-test. So what I've done here is I set my seed, and when you set a seed, you're essentially setting a seed for the random number generator. And what that means is that it allows for you to reproduce other people's research because you're starting from the same seed when you generate any random numbers. And so what I'm doing is I'm simulating a sample of 28 people where the average heights of that group is 69 and the standard deviation of those heights is 4. And so I'm going to run this, and that's going to give me the heights. And if I look at heights, it's just a list of different observations. You know, this person's height was 66 inches here, and this one's 75. We're switching to inches just to be fair. And then, because we were doing centimeters beforehand. And so now we elicit a null hypothesis, and the null hypothesis is called mu naught. That's how I've defined it. And so mu naught, or the null, is that the average height is 66.5 inches. Well, we go ahead and we calculate our mean. Our mean winds up being 68.78. And so we're simulating from a distribution that has mean 69 and standard deviation 4. So that doesn't mean we're going to exactly get that. We're only taking 28 samples. So if we took 28,000 samples, we'd probably get something pretty close to 69. And we calculate the standard deviation of that. And then we obviously try to figure out how many observations we have, which we know is 28. And then we calculate our t-statistic, and it's exactly the mean subtracted off by subtracting the null off divided by the standard error with the sample standard deviation used. Our degrees of freedom is n-1. And now we calculate our p-value. And so we haven't really discussed in depth what a p-value really is, but we've definitely talked about concepts that you needed to know to understand it. And so the p-value here we know is the probability of getting the observed or more extreme outcome, right? So we observed an x bar of our mean of this amount, and we have a t-statistic that we calculated from that. And so the p-value is going to be the probability of us observing this mean or something more extreme, given that the null hypothesis is true. And so we were doing a two-sided test. If you remember our video, we explained what a two-tailed hypothesis is. Two-tailed hypothesis test is. So we're going to calculate what is the probability of getting this on one side and the area under the curve that is more extreme on one side, and then multiply it by 2. And we'll explain that just very shortly. And so we calculate our p-value, we have our test statistic, and now remember we're supposed to elicit a significance threshold beforehand. And so my significance threshold is the probability that if the probability of us observing this difference in mean right here from the null, if the probability of us observing this is lower than our significance threshold, then we reject the null. And so in our case, a common significance threshold, we usually elicit it at the beginning, is 5% or 0.05 probability. And so in this case, we get a p-value of 0.004 and a test statistic of 3.13. And how you can read that is that the probability that we would have observed a mean of this quantity, 68, given 68.78, given that the null is 66.5, the probability of us observing that or a more extreme outcome, less than or greater than the same extreme, more extreme outcome, is 0.004. And that's lower than a 0.05 chance, and so, or 5% chance. And so we would reject the null hypothesis in favor of the alternative, which is that the true population mean is not equal to the null, because we're doing a two-tail, and not equal is for the two-tail. And so I have a histogram here of our sample, and so you can see this is sort of about how our sample is made, or how the distribution of our sample looks. And we can do this in R just using the t.test function as well. We could pass in our data for heights here, which was our simulated sample, and then our hypothesized mean, mu naught, and then we can get a result that's going to give us the same thing. We have degrees of freedom 27 because we have 28 samples minus 28 observations minus 1. We have the same test statistic, right? We have the same p-value, and so right here at a 95% confidence interval it generates, and it says that it actually rejects it. It gives us the alternative hypothesis that the true mean is not equal to 66.5. It defaults to the two-tail, and it says that we rejected the null at a significance level of 0.05. And so I think let's go through explaining what a p-value really is. And so I'm going to show what a t-distribution looks like given our degrees of freedom of 27. And so at a 5% significance level, what this means is that we got a t-statistic, right, of 3.13. And so under a t-distribution with mean equal to 0, that would put us somewhere outside here, right? And so you can imagine a line being drawn right here. I didn't do that in the plot. But the area under the curve to the right of that is the probability of us getting a t-statistic of this size or greater. And that would be fine. We would use that area under the curve, or that p-value, that's what that is. It's a p-value right there, to determine, we would use that if we only wanted to do a one-tailed hypothesis test where we only cared if the mean was greater than the hypothesized mean. But we care about it just not being equal, right? Our alternative hypothesis is that the global population mean was not equal to the hypothesized mean. And so we care about, any values that are extreme enough that they are definitely greater than it on this side, and any values that are extreme enough that are definitely less than it. And these values signify, they may be less than or greater than, but they definitely signify that it's not equal to this, right? It's too extreme. And so we use this area under the curve, and then we also use this area under the curve, and that's why we multiply by 2 here to get this area under the curve, multiply by 2 to get this one as well. And so that's what I mean, this area under the curve. So our significance threshold of 5% for a two-tailed hypothesis are these blue lines here. So if we get any t-statistic that is to the left of this blue line or to the right of this blue line, then we reject the null. And so this is our significance threshold, these blue shaded areas, and then anything to the left of that or to the right of that inside the blue shaded areas causes us to reject the null hypothesis in this case. And so also to drill home, this right here is a plot of the t-distribution. As the degrees of freedom changes, we talked about this beforehand in a handwritten example, but this purple line, if you can see it, is the normal distribution. And then this blue line is the t-distribution with degrees of freedom equal to 1. And so this is actually a sample size of 2. This is incredibly small. I wouldn't use a sample size of 2, but this is what the t-distribution looks like with degrees of freedom equals to 1. And you can see that as the degrees of freedom goes to 10, we get to this red line. And as degrees of freedom goes to 50, we get to, you can barely even see the difference between it and the normal distribution. So as our sample size increases, our degrees of freedom gets higher, and then and the t-distribution starts looking more and more like the standard normal. And so that's how we express our confidence in our larger samples, right? By just converging to a normal distribution. And all right, so now let's do a 2-sample t-test. And so in a 2-sample t-test, we have 2 samples. They're independent, right? So they're not not related to each other at all. And here, the thing about an independent 2-sample t-test is it assumes that the groups have equal variance. And if they have unequal variance, then you have to do some modifications, but we're not going to go into that sort of depth. But here, we're going to simulate 2 groups, and we're going to calculate both of their means. We're going to calculate both of their standard deviations. We're going to obviously get both of their sizes, which we already know it, but, and so now we calculate our t-statistic, our degrees of freedom, and our p-value, right? Our degrees of freedom, we didn't go over this, but the degrees of freedom is slightly different in an independent 2-sample t-test. You take the sample size of the first one plus the sample size of the next one minus 2. And that kind of makes sense. In a 1 sample, we take the sample size minus 1, but now we have 2 samples. So now we need to take the first sample minus 1 plus the second sample minus 1, sample size minus 1, and that's going to be the sum of their sample sizes minus 2. And so that's degrees of freedom. This is our p-value because we're doing a two-tailed hypothesis test. We look at our t-statistic and our p-value, and we have a t-statistic of 3.28 and a p-value of 0.0018. And if we do the significance level of 5%, we would reject the null hypothesis at this point. And then we can also do this in R by just passing the two groups in, and it will go ahead and run a Welch two-sample t-test. It'll take the difference between the two groups, and you can see that we get the same t-statistic and the same p-value, and we rejected the null, that the true difference in means is not equal to 0. And you can also plot this, right? So we can do a box plot between the two groups, and you can see there's quite a difference between group 1, its mean, which is right here at this red line, and then group 2, which is mean is right here at this red line. Remember, the black line is the median. It's not necessarily the mean. And you can see they're quite different, and so that makes sense. So you would think that the heights or the means between these two groups, they're not equal to each other. So you can honestly see visually that this is a fair result to reject the null, that they're equal. So before we head off and learn about regression, first I'd like to talk about correlation. So correlation is a way to measure the strength and the direction of the linear relationship between two variables. So for example, like you see the scatter plot here on the right, this is a cloud of points that is plotting one variable on the x-axis against another variable on the y-axis. And as you can see, as the variable on the x-axis increases, the variable on the y-axis decreases. And I would say that this right here, these 2 points have a fairly strong negative correlation. And so the most popular correlation coefficient you'll see is the Pearson's correlation coefficient. It ranges from -1, which would be like a perfect negative correlation, to a +1, which is like a perfect positive correlation, with 0 indicating that it's just, they have no relationship at all. It will practically look like random noise if you plotted the scatter plot. This one right here, just off the hip, would probably be somewhere around -0.5 to -0.7, just looking at it, and just to signify that it has a fairly strong or moderately strong negative correlation. And so this is the formula for the Pearson's correlation coefficient. Essentially, on the numerator side, what we're doing is we're taking each of the data points for the x variable and subtracting off it from its mean. And then we're taking each of the data points from the y variable and subtracting it off from its mean. And then we're taking the product of each one of those, multiplying them together, and then summing it all up. And so the numerator just takes the sum of all the products of each variable's dispersion from the mean. And then in the bottom half of the denominator, we're essentially doing the same thing, except now we're squaring the dispersion and summing them up individually, and then taking the square root. So we'll take each x data point, subtract it off from its mean, and then square it, and then sum all those up first. And then over here, we'll take each y data point, subtract it off from its mean, square it, and then sum all of them up first. And then once we have both the sum on the x side and the sum on the y side, we'll multiply it together, and then we'll take the square root of that. So that's how that works. So like I said, I showed you over here, this is a scatter plot. Scatter plots are really popular in statistics, and it's a common way to visualize the relationship between two variables. So we can calculate it using the correlation coefficient formula, or we can visualize it. And in a lot of cases, visualizing it is good enough to be able to determine if there's a linear relationship. And so one thing to remember is that correlation does not imply causation. Just because in this graph right here, just because as this x-axis variable, the x variable increases, this y variable decreases, does not mean that this x variable causes the y variable to decrease. That's very important. It's just negatively associated is how we call it. And so why is that the case? It could be the case that there is some other variable that's not included in here. Say there's a third variable that's not included in our chart that's actually affecting the relationship between the x variable and the y variable. And so without that other, like what we call confounding variable, then maybe we wouldn't even have this negative relationship. And so that's why we don't say that. And there's ways of determining causal what we call causal inference, but that's a separate course and that's a topic for a separate day. And so let's see how to test correlation in R. And so what I'm going to do is I'm going to simulate some synthetic data. Synthetic data is actually a really good way to understand these concepts. If you can simulate your own synthetic data, make some assumptions about its distribution, you can learn a lot about how these statistical concepts can apply to different types of data. But so what I'm doing is I'm creating a synthetic data set that shows the relationship between advertising expenditure for a company and the sales revenue for that company. And so as you can imagine, you would imagine to see that as companies spend more on advertising, they tend to make more money. And obviously there's other things in there that could affect that relationship, right? But this is a decent example. And so what we're going to do is I'm going to use ggplot to plot the scatter plot, which we already saw up here, but I'm going to do it again. And right here we have advertising expenditure on the x-axis, sales revenue on the y-axis, and every single point, like for example this point right here at right here would be this company had spent somewhere around $7,000, could be $7,000 a month or $7,000 a day or $7,000 a year, depending upon how small the company is or large it is. But it's spent around $7,000, and as you can see at this point, it has sales revenues somewhere around $25,000, and then here it spent around a little bit, almost close to $10,000 here, and then had a little bit over $40,000. And so this right here, I'm pretty confident is a strong positive correlation. And if we take the correlation coefficient between sales revenue, this is how you do it in R, using the core function as a built-in function of R. Obviously we use it a lot, so R already has it prepared for us. You can see that the correlation coefficient is 0.945, and that is really high. That's near 1, that's near perfect correlation, and I believe the chart reflects that. And so in the next video, we're going to hop in and do linear regression, starting with simple linear regression. So we just learned about correlation, and so now I think it's a perfect time for us to start talking about simple linear regression. And so simple linear regression, or just linear regression in general, is a method to use to be able to understand the relationship between two variables. And essentially what we're trying to do is we're trying to figure out what is the line of best fit between these two variables. So as an example, you remember we plotted the scatter plot of the advertising expenditure and sales revenue. We saw that it had a strong linear relationship. The correlation coefficient wound up being close to 0.95. And as you can see, we have this red line that goes through the cloud of points. That red line is the line of best fit, and it was learned, learned in quotation marks, it actually is learned using automatically. There's a built-in function R that'll do it for you, but it's essentially learned using linear regression. And now, so in linear regression, there are two types of variables. We have our independent variables, or our explanatory variables. These are the variables that could be one or more. In simple linear regression, we're only using one explanatory variable that predicts, or is supposed to be used to explain or predict, the dependent variable. So the explanatory variable is usually our X variable, and the dependent variable is our Y variable. That's how you'll usually, if not all the time, see it referred to as. So for example, in our sales revenue and advertising expenditure example, sales revenue would be our Y variable, or our dependent variable, and advertising expenditure would be our X variable, or our independent variable, or explanatory variable. And so right here you have the Y that you're trying to learn. You're trying to learn this Y, or Y hat, that is as close as possible, that is the best fit through these clouds of points. And it's a straight line. That's why it's linear. It's a straight line. And you're going to do it by learning an intercept term. You can do it where you don't learn an intercept term, but we're going to stay simple here and just use the intercept. And the intercept term is going to determine the height of this red line. And so the next thing that we learn is the first beta coefficient. We call them beta coefficients on our explanatory variable, which is advertising expenditure. And this coefficient, in coupled with the y-intercept, essentially what this coefficient gives you is the slope of the line, right? It's going to be if you remember rise over run, it's going to be the slope of the line. And so for how you can read this is that we have our X variable here, which is our explanatory variable, which is our advertising expenditure variable. And for how you can read this is that for each additional unit increase, like one unit increase of advertising expenditure, we get a beta 1, the first beta coefficient increase in sales revenue. And so that's what it means for the slope of this line. And this error term right here is the difference between each of these points and the line of best fit. And so with linear regression, we have some assumptions that have to be met. And these are the assumptions that you'll see. Linearity, right? So we're fitting a linear line. So we need to make sure that there's a linear relationship between our independent and dependent variables, between advertising revenue and sales revenue, or advertising expenditure and sales revenue, sorry. And we need to make sure that relationship is linear before fitting a linear model like linear regression. We need to make sure of these two. These are, and I'm going to show you how to test these very quickly. Independence. So we need to make sure that the residuals, right, which is the difference between our observed, which is our actual values, and the ones that are predicted by our model, are independent. There shouldn't be like any two residuals for like observation number 4 and observation number 5 to be correlated in some way. Or there shouldn't be, when I plot the residuals against the fitted values, which you'll see, there shouldn't be any relationship. As we shouldn't see anything where the higher the values that we predict, the bigger the error of the residuals. We shouldn't see that. That means that there's something wrong with our model, and that'll make more sense once we start plotting these. And homoscedasticity is the next one. We want to make sure that the variables, the residuals, as we plot them, we'll commonly plot them against the fitted values, the ones that were predicted, the predicting values, and make sure that they don't have any the variability between them doesn't increase as we predict higher and higher values or something like that. We want them to just be just uniquely or just scattered around 0. Which you'll see what that means. We want to make sure that our residuals are normally distributed. And if we're doing multiple regression where we have more than one explanatory variable, we want to make sure that there's no multicollinearity. And what that means is that if we have one explanatory variable and another explanatory variable, and we're trying to use those to predict our dependent variable or our y variable, we want to make sure that these two explanatory variables are not correlated with each other, because that could negatively influence the coefficients we learn from our model. And so let's dive into R to see how this is actually applied, and a lot of this will start making more sense. So remember, this is the scatter plot generated by our linear regression model. And here what I'm going to do is we had our sales revenue and advertising expenditure data. I'm just going to fit a linear model to this data, right? And I'm just using the LM function. It's called linear model. R already has it built in because it's used so commonly. And we can print a summary of this model. And so if you remember, if you noticed, the sales revenue we made it a function of advertising expenditure, where we said it's going to be 5 times whatever the average, each sales revenue point, it's going to be 5 times whatever the advertising expenditure was at that point, plus some random noise. And so as you can see here, we printed out a summary of the model, if you can see down here, and it gives you your formula. Right here we printed the summary. And also, what it does is it gives you some statistics about the residuals as well, given the median and the quartiles, etc. But more importantly, we have our coefficients down here. We have that the intercept that we actually learned is -40, right? And what it does is, and we also learned a coefficient for advertising expenditure that's close to 5. And so that's really close to what we actually, is the ground truth reality, because we created this. And what I think is interesting is that it actually learns if a standard error, or it calculates a standard error. It doesn't learn it; it calculates a standard error, and then it calculates a t-value, and then it calculates a p-value, right, for these, and it tests the significance of this coefficient. And so what that really means is that we learned about what a t-test is. We're gonna learn these coefficients, and what it's doing is it's learning this coefficient 4.95. And then it's conducting a t-test on it, a one sample t-test on it, to see if this 4.95 is different enough from 0, which means there's no effect, different enough from 0, to be able to reject the null hypothesis, which is that it's zero, that it has no effect on the dependent variable. And as you can see, it's 4.95, it's almost 5 away from zero. It's got a standard error of 0.17. We calculate standard error the same way, sample standard deviation divided by the square root of the sample size. And then we calculate our t-value the same way using a t-distribution. And then we can calculate a p-value. And here, this is really significant. And so here we use 98 degrees of freedom. We had 100 observations, and so the t-distribution has 98 degrees of freedom because we subtract off 1 degree of freedom for the intercept, and we subtract off 1 again for advertising expenditure coefficient. And that's how it kind of works when we do a t-test in linear regression. And then again, the p-value is really low. The one thing we need to take note of is the adjusted R, or actually in this case, what only really matters is the R squared, right? And so what R squared is essentially we're going to calculate the correlation between these two variables, and then we're just going to take that correlation and square it. And so this R squared should essentially be the correlation between these two variables squared. And the adjusted R squared that we learned here is going to adjust for the number of explanatory variables we use in our model. And so it's going to kind of penalize us for the number of explanatory variables we use. And that kind of keeps us from using, it kind of adjusts our accuracy measure, which R squared is a measure of accuracy. It's going to adjust our accuracy measure based on how many variables we include in our model. And so R makes it really easy to diagnose our model to see if it meets the assumptions of linear regression. And so the first plot that we get is the residuals versus fitted values. And here what we're testing, this plot is going to be all the values that we predicted for all the observations right here. And then on the y-axis is going to be the error that we got. And so this is one observation, pick a dot here. This is for a particular observation. This is what we predicted. And then this was what was the error for that particular observation. And it plots that for every single observation. And what we're testing here is, are the residuals independent, and is there any heteroscedasticity, right? And so if it's independent and there is no heteroscedasticity, then we should see it just kind of randomly distributed around this line at 0, and this red line tests that slope. And as you can see, the red line should be fairly flat, and it's pretty close to being flat. If there was some heteroscedasticity, what that means is that what you'll see these cloud of points be very close to 0 here, get a little bit wider here, a little bit more dispersed around 0, and then here you'll see them really dispersed around 0, and they'll sort of fan out, and that's not a good thing. And so the next plot is going to be our normal QQ plot. And this is a way for us to test the normality of our residuals. We're going to take the residuals, and if they were perfectly normal, you would see all these little black points be on this line perfectly. And it sort of deviates a little bit from normality, but it's not enough to where I would say that we don't meet that assumption. The next plot is called scale and location. And it's another way to test our assumption of homoscedasticity, or to see if there's any heteroscedasticity. If there is any heteroscedasticity, that means the variance changes, then we would see it start to fan out as we get to larger values. But it looks like it's equally distributed at any values of fitted values. It's equally distributed all across. We'll see it get larger and larger and more dispersed from the line as we get into bigger fitted values. So that's a good thing. The last plot that we have is the residuals versus leverage. And so this is a really good way of seeing if there's any points, if there are a lot of points that affect the slope of our line. And so if there's any points that are outliers, they can dramatically affect the slope of our line. And so it sort of flags these points for us, 85, or the number of the observation number 20, observation number 89, observation number 85, to see if it dramatically affects that line. And so that's how you can actually do these 4 plots and how you can interpret them to be able to test the assumptions. And this is how you can conduct a linear regression, run a linear regression model on your data using R. So we just learned about simple linear regression, where we took one explanatory variable and we learned a linear relationship between it and a dependent variable. We're going to talk about multiple regression, and multiple regression is when we have 2 or more explanatory variables and we're trying to fit a linear regression equation, or learn a linear regression equation that produces the line of best fit, or in our case, the plane of best fit to the data. And so beforehand, we just had the y-intercept, beta naught, and then beta 1 times the first explanatory variable, and that was it. So simple linear regression was just this formula here. Multiple regression is going to extend to more than one explanatory variable, learn a beta coefficient for all of them. And well, I forgot, we definitely still have this error term here, which is the residuals, or the difference between the y, or we call it y hat, that we learn, and our actual observed response variable. And so the y is still our dependent variable. These are, all the x's are still our independent variables. We just have a lot of them now. Beta naught is still our y-intercept. Each beta coefficient is just a respective coefficient for that explanatory variable. And our error term is also our residual still. And so let's step into R to see how we can do or extend our current problem of advertising expenditure to predict sales revenue to a multiple regression case. And so here I am in R. I've added prices as a new explanatory variable, and this is going to represent the general prices of the goods that the company sells. And I modified our sales revenue equation to be 5 times advertising expenditure like before, but -3 times prices, because you can imagine that as prices increase, the demand for those same goods will go down. And so if they're charging a lot for their goods, it may be harder for them to sell. And then we're going to tack on some random noise that's unexplainable. And so that is going to be sales revenue. I'm going to do prices again just to be safe. We create a new data frame, and then we plot it using GG pairs, which comes from the GG Galley package. So what GG pairs does is it plots a correlation matrix where everything on the right is on the y-axis and everything on the top is on the x-axis, and the intersection is the scatter plot between the two. So right here, this little plot is going to be the advertising expenditure on the y-axis and then sales revenue on the x-axis. It doesn't really matter here which one we choose, but you can, whether one's on x or one's on y, it's still going to be the same. As you can see, there's a positive relationship between the two. Here, though, we see prices and sales revenue. The relationship is fairly negative, but not as strong. Not a strong relationship, but still there's some there. And then here we can see that there's no relationship between prices and advertising expenditure. And so that's good. There's no multicollinearity right there. And so you can see that the correlation coefficient between advertising and prices is 0.087, which is negative 0.087, which is practically 0. And then these two are, you can tell that sales revenue and advertising expenditure and prices are fairly correlated with sales revenue. The intersection of these right here, the diagonal, is the distribution, right? So it's going to take all of sales revenue and just plot the probability density function for it. And it's going to plot a density for them. And you can see these are the densities for them here. And so we can fit a linear model doing the same thing as we did beforehand. We take sales revenue, we model it as a function of advertising expenditure and then prices using our data. And we learn our model. We can print out a summary. I think I'm a little bit out of view here. There we go. And so as you can see, it learns almost a 5 for advertising expenditure and then almost a -3 for prices. And so that's good. And it finds that both of them are significant, which is also good. And it uses 97 degrees of freedom because remember, we take off one, we have 100 observations. We take off 1 for the intercept, 1 for advertising expenditure, and then now another for prices, and we get down to 97 degrees of freedom for our t-distribution. And our adjusted R-squared is really high, even when adding in that explanatory variable and adding in that penalty for it. It actually still wind up giving us a better predictor. It becoming a better predictor of sales revenue. And this is a really good model. Granted, it's synthetic data, so I hope it's good. And so now I'm going to show you what this looks like. I said we learned a line of best fit, right, for the simple linear regression. But we're going to learn a plane of best fit for multiple regression. And so the plane that we learn, I'm going to pass it into here to plot our model, and we're using scatterplot 3D to do it. But this is the cloud of points where we have advertising expenditure here, prices here, and then where these two intersect is going to be the revenue for this. So we're going to have this advertising expenditure, this price, and then this revenue for it. And then the plane right here is going to be the actual equation that we learned for from using the LM function here and built in an R, linear model. And so that's what we're actually learning. Since it's 3D, we're now learning a plane. Obviously, if we get up to, we have 3 explanatory variables and 1 dependent variable, I wouldn't be able to plot 4 dimensions, unfortunately, but this is how it would look in 3D, and this is a good visualization of how we're learning a hyperplane or a plane instead of a line of best fit. It's a plane of best fit through the points.